Hello everyone and welcome to a new lecture of the Strategic Learning in Wireless Networks course. In today's lecture, we will talk about decentralized learning over graphs. This is the outline of today's lecture. First, we will briefly discuss how important is decentralized learning over graphs and define the learning problem. Then we will go over a short overview of graph theory. Note that this will be very brief, as the focus of the lecture is not about graph theory. We will simply go over the relevant notions to the decentralized learning problem. Then we will discuss two communication efficient framework, cooperative SGD and matcha. Finally, we will talk about compression schemes in general and show how they can be used in the context of decentralized learning through the Surco Sgd algorithm example. To emphasize on the importance of the decentralized learning problem, let's start by discussing why the parameter server setting, where a set of devices are communicating with a central entity, is not very practical. First, when the devices are moving or communication takes place via multi-hop relays, the exchange of information between the parameter server and the devices can be expensive. Moreover, there are privacy and secrecy consideration, as the devices may be hesitant to exchange information with a remote center. Finally, the efficiency of the learning algorithm depends on the slowest device, since as the number of devices increases, the uplink communication resources becomes the bottleneck. That is why it is more practical to exchange information in a decentralized manner, and this can help to avoid high latency in communication costs, especially as the number of IoT devices is expected to be over 75 billion by 2025. Now let's introduce some notation and define the learning problem. In this lecture, we consider a set of M interconnected agents or nodes. Each node has access only to its own local data set DI, and these nodes aim to train a model collaboratively using the joint dataset by minimizing the objective function f defined in equation 1, where x denotes the model parameters. It could be, for instance, the weights and biases of a neural network. Fi of x is the local objective function. S denotes a single data sample, and Lxs is the loss function for sample S. As highlighted in the introduction, we look not only to solve the learning problem in a decentralized manner, that is in the absence of a central unit, but also we are looking to solve this problem in a communication efficient manner. Generally speaking, there could be different ways to improve the communication efficiency of distributed learning. The most promising and often sought directions are first, performing more local work. That is, the nodes use their own dataset to update their models for a certain period of time, and then they exchange with neighbors periodically to encourage consensus. As an example, we will discuss later on cooperative SGD. Second, parallelizing the communication between nodes by decomposing the base graph into subgraph, as done in Matcha, for instance. Finally, by compressing the information exchanged between the nodes as performed in Surco Sgd algorithm, for example. Before proceeding further, I would like to highlight that in this lecture, we mainly will focus on primal first order methods. As mentioned earlier, we will start first with a brief overview of graph theory. A graph is a way to formally represent a network of connected objects. In terms of notation, a graph is an ordered pair of two parts. V, the set of agents or vertices. The cardinality of this set is equal to M to be consistent with the notations used in the definition of the learning problem. And the second part is the set of edges or links. If there exists an edge between two agents I and J, then the couple IJ belongs to the set of edges. Let's take the following example. Here we have 8 vertices and 7 edges. The vertices are V1, V2, V3 till V8. And the set of edges is formed by the couples of or pairs of vertices that have links between them. For instance, edge V3 has a link with edge V1. That is why the first element in this edge set is V1, V3. Now we will go over some basic definitions. We say that a graph is simple if it doesn't contain any self-loop nor multiple edges. For instance, graph A is simple, whereas graph B here is not simple, since vertices V2 and V3 have self-loops, and vertices V4 and V5 have multiple edges. A graph is said undirected if all its edges are bidirectional. That is, the origin and destination are not fixed in the path between 2 points A and B. For instance, graph A is undirected graph while B is a directed graph. Notice that in this graph B, the edges have direction represented by an arrow specifying the flow of information from the origin to the destination. In this case, the elements of the edge sets are tuples, not sets, since the order does matter. For instance, the link between V6 and V2, the flow of information is from V6 to V2, not the other way around. And that is why we find the tuple V6, V2 as part of the edge set. Whereas in the first example A, we have an undirected graph, which means that information can go from V2 to V6 or from V6 to V2. A path between two vertices I and J of length n is defined as the ordered sequence P0, P1 until Pn, where we start from the origin P0 equal I, and we end by Pn at the destination Pn equal J. For each integer t in 0 n minus 1, we have pt, the tuple pt plus 1 belongs to the set of edges. With this definition, we say that a graph is connected if there exists a path between all possible Asian pairs. For example, graph in the example A, the graph is said to be connected, while B is a disconnected graph since there is no path between V6 and V1, for instance. We define the neighborhood of an Asian N as this the set n capital N small n as the set of vertices G such that there is an edge between N and G. The degree of Asian N is simply the cardinality of its neighborhood, that is the number of his neighbors. Note that a graph can be fully represented mathematically by its adjacency matrix A. Each element Aij is equal 1 if the pair Ij belongs to the set of edges and 0 otherwise. Let's take the following example. Here, for instance, the neighbors of V2 are V3 and V4. That is why the neighborhood N2 consists of only two elements, V3 and V4. And hence, the degree of V2 is equal to, which is the cardinality of the set N2. As for the adjacency matrix, the adjacency matrix of this graph is given by the following matrix A. Let's take the first row, for example. So this first row corresponds to V1, so the neighbors of V1. And since V1 has only two neighbors, which are V3 and V4, then we have 1 and 1 in the last two elements of the row, whereas we have 2 zeros in the first elements because V1 does not have a self loop and it doesn't have a link to V2. Similarly, we can obtain the other rows by examining the neighbors of V2 for row 2, V3 for row 3, and V4 for the last row, the fourth row. A graph is static if it does not change over time. That is, the adjacency matrix A is always the same at any given instant. When A does change over the time, then the graph is said to be dynamic. We define the degree matrix as the diagonal matrix D, whose entries are the degree of each vertex. The graph Laplacian matrix is defined as the difference between this degree matrix and the adjacency matrix. L is a positive semi-definite matrix, and its eigenvalue can be ordered and represented as follow. So it's from lambda 1 less than lambda 2 to lambda m, where lambda 1 is equal to, it can be shown that lambda 1 is equal to 0. And the second smallest eigenvalues of L is known as the algebraic connectivity, which is lambda 2 of L. And a larger value of lambda 2 implies that we have a denser graph. Finally, if lambda 2 is strictly positive, then we know that the corresponding graph is connected. With this, we end the first section devoted to the graph theory overview, and we go back to the decentralized learning problem over graph. And we start first by discussing the main ideas behind cooperative SGD. Cooperative SGD is a general framework that englobes a wide range of SGD type algorithm. Some of them are parameter server specific and other are decentralized. The notation of the algorithm is given as follow. So we have A of tau W and U, where tau is the number of local updates. W is the mixing matrix, that is the matrix used to perform model averaging, and U is the number of auxiliary variables or anchor models. The mixing matrix plays an important role in the decentralized learning problem over graphs, since it ensures that the nodes reach consensus in terms of converging to the same stationary point. Quite often it is assumed to be symmetric, that is W transpose equal W, double stochastic, which means that W times the 1, where 1 here is the vector of all ones, is equal 1, and 1 transpose W is equal 1 transpose. Here's this equation translates to like the sum of across rows and columns needs to be equal 1. Also, it has positive diagonal, means WII is strictly positive because every node needs to incorporate its own model in the mixing, and edge utilizations property, which means that if edge I has a link with edge J, then the associated weights is strictly positive. Otherwise, it's equal to 0, which makes sense. It means that edge I will only use the information coming from its neighbors. For an undirected graph, which is the main focus of our lecture, these assumptions can be satisfied if we construct W using metropolis weights, for example. So here Wij is equal 0 if Ji doesn't belongs to the set of edges, and also if J is different than I. If J is a neighbor of I, then Wij is simply equal 1 over 1 plus the maximum between the degree of I and the degree of J. And the only remaining term for the row, ith row is Wii, which is simply equal 1 minus the sum of the corresponding weights of its neighbors. To give the update of cooperative SGD, we start by defining the following quantity. First, we define the model versions at nodes in one matrix xk, where here k denotes the number of iterations. As you can see, we are introducing anchor models or auxiliary variable zi here. Next, we define the gradient matrix jk by concatenating the gradient of every loss function with respect to the its model xi. Note that the gradient at the auxiliary variables zi are equal to 0 since they are only updated by averaging a subset of the local models. At iteration k, the local models and auxiliary variable are averaged with neighbors according to a time-varying mixing matrix. Note that Wk is time varying in order to capture the periodic averaging of the algorithm. In fact, the identity matrix I here of order m plus nu means that there is no internode communication during the tau local updates. Only when k mod tau equal 0, that is, every tau steps, the nodes exchange information with their neighbors using the mixing matrix W. Finally, the update rule is given as follow. Xk plus 1 is equal to the difference between xk and jk, eta gk, where eta here is the learning rate, times the mixing matrix wk. Now we show how that many existing communication efficient algorithms are special cases of the general cooperative SGD framework. In fact, if we set tau equal 1, fix the mixing matrix W equal to 1 times 1 transpose over M, and set nu equal 0, that is the number of auxiliary variables are 0. Then we get the fully synchronous SGD. The per node update simplifies to equation 4, where here all xi are equal to a common variable xk. And note that this is a parameter server setting where a central entity is communicating with m nodes. Now, if we fix W to be 1 times 1 transpose over M, and again nu equals 0, but we consider a general tau, then we get the periodic averaging SGD, or also known as local SGD, and the per node update is given by equation 5. Here also it's a parameter server setting, and every local agent or nodes has a copy xi that is exchanging with the parameter server every tau iteration. If we set now tau and nu to be equal 1 and consider W to be of equal WA, where A is a scalar and the matrix WA is given by equation 6, then we get the elastic averaging SGD, and the per node update in this case is given by equation 7 and 8, where here X bar is simply the average model, and Z here is an auxiliary variable kept at the parameter server and shared with the nodes. Finally, if we set tau equal 1, consider a general matrix, mixing matrix W, and set nu equal to 0, then we get the decentralized parallel SGD, and this corresponds to the decentralized setting. We can see in equation 9 the per node update, and it has two components. The first part is obtained by mixing the model of node I with its neighbors. And the second part is simply running one SGD step. Before stating the convergence guarantees of cooperative SGD, let's start first by summarizing the main assumptions. So the first assumption is that we assume capital F to be smooth. That is, the difference, the norm of the difference between the gradient is upper bounded by L, the Lipschitz constants, times the difference between X and Y. We assume that F is lower bounded by a quantity that we denote by Fm. The stochastic gradient G are assumed to be unbiased. That is, that the expectation of these J of X is equal to the gradient of F of X. Also, we have the assumption of bounded variance, which is that the expected value of the difference between G of X and the gradient of F of X in norm square is less than a constant, positive constant sigma square. These are common assumptions that we already talked about regarding the mixing matrix. That is a symmetric one, and that is double stochastic. And finally, the eigenvalues magnitude of the mixing matrix. We're assuming that the maximum between lambda 2 and lambda m plus nu is less than lambda 1, which is equal, which can be shown to be equal 1. Next, we introduce the following notation and definition. First, we define the average model UK to be equal xk times the vector of 1 of order m plus nu over m plus nu. Note that if this is simply the average of the models XA and ZI, the effective learning rate is equal m times nu over m plus nu. So in case nu is equal 0, this is simply or reduces to the learning rate eta. And we define the parameter zeta to be the maximum between the eigenvalues lambda 2 and lambda m plus nu. From assumption 6, we know that this parameter zeta is between 0 and 1. And we say that an algorithm achieves an epsilon suboptimal solution for a convex function f if equation 10 is satisfied. That is the expected value of the average square norm of the gradient of f evaluated at the average model is less than a constant epsilon. And this inequalities guarantees that the algorithm converges to a stationary point. Under the previously introduced assumption and provided that the effective learning rate eta f satisfies the following equation, and that all local models are initialized at the same point u1, then the average square gradient norm after k iteration is bounded as follow, where the upper bound can be decomposed into two parts. The first one is the same as the optimization error bound in fully synchronous SGD, and the second one is the network error. The error floor at convergence, that is when capital K goes to infinity, is given by equation 11. The network error is a result from performing local updates and reducing inter-worker communication. When all local models are fully synchronized at every iteration, that is when tau equal 1, zeta equals 0, and nu equals 0, the network error becomes 0. The error floor at convergence depends on both parameter tau and zeta. In fact, the bounds will monotonically increase along with both. And we can see that it can be shown that zeta is linked to is related to the mixing matrix W, in the sense that a sparser matrix means a larger value of zeta. In fact, when there is no communication among local workers, then this corresponds to the case where W is equal to identity matrix of order m plus nu and zeta equal 1, which is the maximum value of zeta. And when local models are fully synchronized, this corresponds to the case when W is the matrix given by 1 times 1 transpose of order m plus nu over m plus nu, and zeta equal 0. From the main theorem, we know that the network error bound, denoted by NEB here, is function of tau and zeta, and in fact it is linear in tau, and it is proportional to 1 plus zeta square over 1 minus zeta square. And in this figure we can see how the behavior of the logarithm of the network error bound as function of zeta and for different values of tau. And we can clearly see that the network error bound is more sensitive to the changes in the communication period tau than in the changes of the parameter zeta. In figure 2, various hyperparameter setting for training VGG16 architecture for classification on the CFAR10 dataset are evaluated, where here we consider 8 worker nodes. As suggested by the main theorem, the empirical results show that a higher network error, that is a larger value of tau or a larger value of zeta, leads to a higher error floor at convergence. Now we move to the next section, where we will discuss another way of improving communication efficiency by explaining the matcha algorithm. Matcha proposes a clever way to reduce the communication cost of vanilla decentralized Sgd. First, let's revisit the update of decentralized Sgd given in equation 12. This consists of 2 parts. First is the local gradient step, and the second part is the consensus step, where nodes exchange information with their neighbors. However, one issue with this kind of update is that the delay in performing this local synchronization typically increases with the node degree. Hence, the node with the highest degree in the graph becomes the bottleneck. Thus, the communication time per iteration depends on the maximal degree of the graph, denoted here by delta of G, through a monotonically increasing function T. Without loss of generality, we can assume that the communication sending and receiving model parameters over one link cost 1 unit of time. That is, T of delta is equal delta. A naive way to reduce the communication time is to use periodic decentralized SGD. In this case, each node performs locally a number of tau model updates before synchronizing with its neighbor. However, this way of performing updates treats all links equally, since after every tau iterations, all edges are active. So the question that arises here is, can we activate edges according to their importance in the graph? Of course, at this stage, it is a bit difficult to define the notion of importance of edges, of an edge in the graph. But as an illustration example, let's consider the following graph. Here we can clearly see that the green edge linking V1 to V2 is more important than the blue edge linking V2 and V4, since the absence of the green link means we no longer can access the information at V1, whereas even in the absence of the blue link, we still have a connected graph. This notion of link importance is exploited in the match algorithm, as it will be detailed later on. In fact, it is more beneficial to communicate over critical links more frequently. Matcha introduces the notion of matching, where a matching is a subgraph in which each vertex is incident with at most one edge. By decomposing the base topology into matching, we can obtain disjoint edges, which allows parallel communication and help save communication delays. In this case, the communication delay is simply equal to the number of matching. It is worth mentioning that matcha analysis is valid for an undirected, connected, and static base graph. Figure 3 here illustrates the different steps of matcha. We will describe in details these different steps in the next set of slides, but just to see the big picture, let's quickly go over this illustration. So basically, matcha has 3 steps. The first step in matcha is matching decomposition. In this illustration, we can see that the basic communication graph can be decomposed into different matching, where each color corresponds to a different matching. In this case, we have 5 matching: G1, G2, G3, G4, and G5. The second step is to determine or to find the activation probability for matching. At every iteration, one or more matching are activated according to this probability P1 till P5. For instance, in this example, at iteration 1, G1 and G5 are activated. Then G2 and G4 are activated in the second iteration. Only G1 is activated in the third iteration. And finally, G1 and G2 are activated in the fourth iteration. And this process continues at every iteration until convergence. Now we will explain every step mentioned in the previous slide with more details. So the first step is, as we said, is matching decomposition. So matcha decomposes the base graph into a total of M disjoint matching. Formally, we write that the base graph G is equal to the union of subgraph G subscript small g for G going from 1 to capital M, where the set of edges is disjoint for every pair of graph. While any matching decomposition algorithm can be used to find these matching, one can use, for instance, the polynomial type edge coloring algorithm in reference 4 that guarantees that M, the number of subgraph, is equal to either the maximal degree node delta G or delta G plus 1. Matchings minimize the effect node degree while maximizing the number of parallel information exchanges between nodes. In fact, since all the nodes in the matching have degree 1, the internode links are disjoint, and these links can operate in parallel. Thus, when T of delta equal delta, the communication time for one matching is exactly equal 1. Therefore, the communication time per iteration will be equal to the number of matching M. The second step is to compute the matching probabilities. In fact, in order to control the total communication time per iteration, Matcha assigns an independent Bernoulli random variable BG, which is equal to 1 with probability PG and 0 otherwise. When BG equal 1, the edges in matching G will be used for information exchanges between the corresponding nodes. In this case, the expected communication time per iteration is given by equation 13, where here we use the fact that the expected value of BG is equal PG. When all PG are equal 1, the algorithm reduces to vanilla decentralized SGD, and it takes m unit of time to finish one consensus step. Let CB be the fraction of communication reduction to compare it to decentralized stochastic gradient descent, which will be referred as communication budget. For example, if CB is equal 0.2, this means that the expected communication time per iteration of matcha is 20% of the time per iteration of decentralized SGD. Since matcha aims to give more importance to critical links, then it solves the following optimization problem given by equation 14. The objective function is the algebraic connectivity of the Laplacian of the expected graph, where LG denotes the Laplacian matrix of the jth subgraph. The first constraint is that we want the expected communication time per iteration to be less than CB times the expected communication time per iteration of vanilla decentralized Sgd, which is equal to m in our case. The second constraint is simply ensuring that the activation probability are well defined, that is, Pg is between 0 and 1 for every g in the set 1, 2 until m. Since the algebraic connectivity lambda 2 is a concave function, then it follows that the optimization problem introduced in equation 14 is a convex problem, and thus it can be solved efficiently. The third step is to generate the random topology sequence. Given the activation probability is determined by solving the previous optimization problem, in each iteration we generate an independent Bernoulli random variable bgk for each matching. Thus, in the kth iteration, the activation topology is given by gk, which is the union of bgk times the subgraph g of underscore g. Note that gk is sparse or even disconnected. It is worth noting that all of this information, that is the computation of the activation probability and the determination of the matching or subgraph, it can be obtained and assigned a priori to worker nodes before starting the training procedure. In order to further optimize matcha for decentralized SGD, matcha uses a specific choice of the mixing matrix. In fact, the mixing matrix of the activated topology at the kth iteration is given by equation 15, where alpha is a strictly positive integer that represents the weights associated to the neighbor's information in the consensus step. In other words, matcha uses an equal weight mixing matrix where each neighbor assigns the same weight to the information coming from each of its neighbors. For example, if node 1 is only connected to nodes 2 and 3, then the first row of W is given by 1 minus 2 alpha, 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 and then the rest of elements are equal 0. Of course, the second element is equal alpha because node 1 is connected to node 2. The third one is equal to alpha because node 1 is connected to node 3. And because we need to have the sum of the weights equal 1 for each row, then the first weight associated to node 1 model is given by 1 minus 2 alpha. It is important to note that in order to guarantee the convergence of matcha to a stationary point of smooth and non-convex losses, the spectral norm rho defined as follow. So it's the norm of the difference between the expected value of WK transpose WK minus 1 over M1 times 1 transpose. This spectral norm needs to be less than 1. The following theorem simply shows that for matcha with arbitrary communication budget CB strictly positive, one can always find the value of alpha for which the resulting spectral norm rho is strictly less than 1, and this guarantees the convergence of matcha to a stationary point. In fact, the value of alpha can be obtained by solving the following semi-definite programming problem, where here L bar is the sum over j from 1 equal to m of pj times lg, and L tilde is the sum from g equal 1 to m pg times 1 minus pg lg, and beta here is an auxiliary variable. Before stating the main convergence theorem of Matcha, we mention here the main assumption used in the convergence analysis. First, it is assumed that the local loss functions fi are smooth with Lipschitz constant L. Second, the stochastic gradient are assumed to be unbiased and that they have bounded variance. Finally, it is assumed that we have bounded deviation of local gradients. Now we are in position to state the main theorem. So assuming that all local models are initialized at the same value x bar of 1, and that the sequence of mixing matrix WK is an IID mixing matrix sequence generated by Matcha, then under assumption 1 to 5, and if the learning rate eta satisfies the following, that is eta times L is less than the minimum between 1 and square root of 1 over rho minus 1 over 4, then after k iteration, the average expected value of the norm square of the gradient of f at the average model is less than the following bound given by equation 17, where the constant d is defined as follow. And as mentioned before, since we proved in Theorem 1 that there exists a value of alpha for which rho is strictly less than 1, then we could show that this constant d is less than 1 over 2. Note that if WK is equal 1 times 1 transpose over M, then in this case rho is equal 0, and the error bound reduces to that of the fully synchronous SGD. When WK is fixed across iteration, then the main theorem reduces to the case of vanilla decentralized SGD. We note also that a lower spectral norm, rho, means better error convergence in terms of iteration. Furthermore, if the learning rate is configured properly, then Matcha can achieve a linear speedup in terms of number of Fokker nodes, matching the same rate as vanilla decentralized SGD and fully synchronous SGD. In fact, under the same condition as Theorem 2, if we choose eta to be equal to the square root of m over k, then after total k iteration, we have equation 18. It is worth noting that when the total number of iteration capital K is sufficiently large, that is the case where capital K is greater than m cube, then the convergence of Matcha will be dominated by the first term, 1 over square root of mk. In figure 4, we evaluate the performance of Matcha with variance communication budget, CB equal 2%, CB equal 10%, and CB equal 15% of compared to vanilla decentralized SGD. When the communication budget is decreased, matcha attains significantly faster convergence with respect to wall clock time in communication-intensive tasks, in particular on CFAR 100, presented in the plot or subplot on the left. Matcha with CB equal 2% can take 5 times less work clock time than vanilla decentralized SGD to reach training loss of 0.1. In figure 5, the training loss is plotted as a function of the number of epochs for different value of CB for 3 different tasks. One can observe that when the communication budget is set to 0.5, that is reducing the expected communication time per iteration by 15%, Matcha has nearly identical training loss to vanilla decentralized SGD at every epoch. Finally, in figure 6, matcha performance is compared to vanilla decentralized SGD and periodic decentralized SGD. The performance of the 3 algorithm is evaluated on different topology with varying level of connectivity. 3 random geometric graph topology having different maximal degrees. So the maximal degree in the first subplot is equal 5, and the middle one is equal 10, and the one on the right is 13. In particular, when the maximal degree is equal 10, matcha with communication budget CB equal 0.4, not only reduces the mean communication time per iteration by 2.5 times, but also has lower error than vanilla decentralized SGD, as we can see here from the red plot corresponds to matcha, where the gray one corresponds to vanilla decentralized SGD. When we further increase the density of the base topology, matcha can reduce communication time even by 3.3 times per iteration without hurting the error convergence. To sum up, we can clearly see that matcha takes less and less time to achieve a training loss of 0.1 compared to the other baselines, vanilla decentralized SGD and periodic decentralized SGD. In distributed training, model updates or gradient vectors have to be exchanged between the worker nodes. To reduce the amount of data that has to be sent, compression schemes have become a popular strategy. The most common types of compression schemes are quantization, which aims to reduce the number of bits needed to represent the data, and sparsification, where the goal is to enforce sparsity of the transmitted data. Either way, the goal of compression is to send a compression version, which we denote by q of x, instead of the whole vector x, where q here is an operator chosen to efficiently represent x. Let's start by going over some basic definitions and examples. First, we say that a compression operator Q is unbiased if for every x in Rd, we have the expected value of Q of x is equal x. In the case where such property is not satisfied, we say that the operator is biased. Let E1 until ED be the standard unit basis vector in RD, and D between brackets denotes the set of integers from 1 to D. Then some compression schemes are rand K, which consists on randomly selecting K out of D coordinates. Top K, which consists on selecting the K coordinates with highest magnitude values. Note that both rand K and top K are sparsification methods. Finally, an example of quantization scheme is the random quantization for a precision level S, and defining tau to be equal 1 plus the minimum between D over S square and square root of D over S. Then the ith component of the quantization operator is given by equation 19, where here psi is a uniform random variable, and the operator sign here assigns -1 for negative values and +1 for positive ones. A common assumption made on the compression operator is that it satisfies equation 20. So basically this says that there exists a parameter delta strictly positive such that we have the expected value of q of x minus x square is less than 1 minus delta times the norm of x square. In the case of the example introduced in the previous slides, the parameter delta can be determined as follows. So for rand K and top K, delta is equal the ratio between K and D. And for random quantization, delta corresponds to the inverse of tau. It is worth mentioning that the case delta equal 1 corresponds to the exact communication case, in other words, in the absence of compression. Going back to the decentralized learning problem, we will go over an example of application of compression schemes, the Surco Sgd algorithm. The algorithm was initially proposed and analyzed for the strongly convex case in reference 6, and then the author extended to the analysis of non-convex case in reference 7. The algorithm has two main parts: the communication part 1 and the gradient part 2. Since both parts are independent, they can be executed in parallel. In line 2, Surco Sgd runs in parallel for all nodes, a modified gossip averaging steps. Then we have a compression step in line 3, where the variable qi is the compression between the xi and xi hat. Then we have the communication part, where each worker will communicate with its neighbors, which happens in line 5. And in line 6, we have a local update step of the variable x hat. Then in line 8 and 9, a stochastic gradient update is run to update the variable xi. It is important to note that in this algorithm, all initial variable xi are initialized initialized to the same input x bar, and that xi hat are initialized for all nodes to be equal 0. Before stating the main theorem, we summarize the assumption used in the convergence analysis. Note that these assumptions are similar to the ones covered in the previous algorithm presented so far in the lecture. And these are standard assumptions, and they happen to be quite often used in the literature. In addition to these assumptions, we have also the assumption on the compression operator introduced earlier. With this, we can present the statement of the main theorem. So under assumption 1 to 6, there exists a constant step size eta, and the consensus step size gamma defined as follow, where here rho is the spectral gap defined as 1 minus the module of lambda 2 of W. Delta is the parameter defined in the property of the compression operator, and beta is defined as the norm 2 of the difference between the identity matrix and W, and this beta happens to be between 0 and 2, such that the average iterates of Surco Sgd satisfies the following, where here f0 is simply the difference between the function f evaluated at x bar 0 minus f star. The constant c is equal rho square times delta over 82, and sigma bar square is the average value of sigma I square. Now we discuss the performance of Surco Sgd for three decentralized learning problem. The first one is the regularized logistic regression on the dataset RC-V1. More details on the experiments can be found in the reference papers. In figure 7, the evolution of the training suboptimality is plotted in terms of the number of epochs in the left subplot, and in terms of the number of transmitted bits in the right one. In both plots, Surco Sgd performance is compared to plain, which refers to vanilla decentralized Sgd, and also to two decentralized Sgd-based algorithm with compression. Difference compression decentralized Sgd DCD, and extrapolation compression decentralized Sgd known also as ECD. For the three algorithms, two types of compression are used, rand 1% and top 1%. We can see that Surco Sgd outperform DCD and ECD in terms of convergence and also in terms of communication savings. It also presents significant savings compared to vanilla decentralized Sgd. In fact, in the right plot, we can see that Surco Sgd is using 100 times less communication than vanilla decentralized Sgd to reach a training suboptimality of the order of 10 to the power minus 2. Similarly, the performance of the algorithm is investigated when we consider quantization instead of sparsification. Here, quantization, the random quantization using 4 bits is used for the compression. And we can see that a similar conclusion can be made when using quantization. In fact, Surco Sgd outperform both DCD and ECD, and it presents significant communication savings compared to vanilla decentralized Sgd. Next, we discuss two non-convex decentralized learning problem. The first one is image classification using ResNet 20 on CFAR 10. In figure 9, the training loss is plotted against the number of epochs in the left and in terms of the size of transmitted data in the middle, while the test accuracy is presented in terms of the size of transmitted data on the right. Surco Sgd is used when the compression operator here is the scaled sign operator given by equation 21, and it's compared to vanilla decentralized Sgd and centralized Sgd. Comparing the training accuracy reached after the same number of epochs, the decentralized algorithm performs the best, followed by the centralized one, and lastly Surco Sgd. However, the test accuracy is highest for the centralized scheme. When comparing the test accuracy reached for the same transmitted data, we can see that Surco Sgd significantly outperform the exact decentralized scheme with the centralized one being the worst. Finally, for the language modeling task, both decentralized schemes suffer a drop in the training loss when the evaluation reaching the epoch budget, while Surco Sgd outperforms the centralized Sgd in test perplexity. When considering perplexity for a fixed volume of data, Surco Sgd performs best, followed by the exact decentralized and centralized algorithms. This brings me to the end of today's lecture. Here we included the references used to make the slides of this lecture, and students are encouraged to check more details from these references if needed. The topic of the next lecture will also cover decentralized learning, but with a focus on primal dual methods.